easier and simpler. So that's an example of system that is quite nasty to model with angles all over the place, and much easier with these approaches. Okay, so now people do optimal control with DAs quite a lot. And essentially when you write an OCP with DAs, it's not a very big difference with the classic stuff. So for example, semi-explicit DA, so you still have your cost function. It may depend on your algebraic variables as well. You have your semi-explicit DA, where Z is part of the game. Your inequality constraints may depend on the Z as well. And Z is part of your decision variables in that sense. You would also optimize over Z, even though Z is somehow linked to the rest via typically this equation here. And you may, for example, impose some initial conditions on the differential states. You would not impose initial conditions on Z, because Z is implicitly a function of X. So you don't have initial conditions for Z at all. You may have also OCPs with so-called fully implicit DAs in this form possibly. So there you have a larger set of equations that basically blend X dot and Z throughout. It's just a different form if you don't have it in this form here. So it's and some people play with high index DAs, but it's a bit more of an academic interest, I would say. In practice, most often people do their best to get an index 1 DA, something that is nice to solve, and then use that in the optimal control problem. I'll discuss a little bit later of problems involving DAs that do not have imposed initial conditions, but something a bit different, or impose initial conditions and terminal conditions, because in that context you get some very strange effects that you need to resolve. And the story of consistency conditions, if you solve OCPs of this form or that form, you don't really have to bother about them. All you have to do is make sure that the assigned initial conditions, this x0 bar, is consistent. So for example, in the pendulum, your x0 bar should be consistent, and then everything will work fine inside the OCP. Okay with that? Okay, so we can talk about multiple shading for the constrained OCP, so how you handle that. So you can imagine that you have, for example, a fully implicit DA, so you have your Z's appearing in here. X dot is a function of, and Z are implicit functions of XU. And let's imagine that you have somehow written an integrator, like a code that would process these equations and give you a simulation of your X's and maybe also your Z's for given initial conditions and inputs. So there we would have the same picture as usual. You may discretize your inputs on a time grid. You would have your discrete states, differential states on the x0, x1, and so on. It's exactly the same picture as in multiple shading before. The only difference is that now you need an integration code that would be able to process that, as opposed to x dot equal f of xu. An example, if you have the DA in that form, semi-explicit. An example of such code could be a simple implicit Euler scheme that would read like this. So you would generate the next x plus here by taking an Euler step. So if you take an Euler step on this OD part, that's essentially xk plus the time interval, could be this thing here, times the dynamics, function of x plus z plus u. So that's an implicit Euler step, and then you want to resolve the z plus via this equation. So you could do that. That would work for an index 1 DA. In general, I don't recommend to use Euler unless you want to do some quick and dirty prototyping, for example. These schemes are not very effective from a computational point of view, but they work anyway. So in principle, it's not the end of the world to write an integrator to process your DAE into an integration function. Does that make sense? Yeah. So this function, it would return x plus. If you take a single step, that would essentially give you, or give an approximation of this function up here, the simulation. You would also get z plus, but you may not care about it in the OCP, not necessarily. It could be that z is just a variable that is somehow hidden inside the code. So in that sense, an integrator that processes DAEs may be kind of hiding these z's from you. Like if you care about only the x, these z's could be just internal variables that run inside your code. So if you have an integrator of that kind, or any decent integrator processing DAEs, then you can form a very classic multiple shooting code. So you have your functions f delivering the simulation for a given xk uk. So the same picture as usual, and you would assemble your NLP as usual. So assign initial conditions and then the shooting gap constraints, and inside these functions the z's will be processed, but remember that the z's are always basically implicit functions of the rest. So for x u given, you're supposed to be able to solve these equations for x dot and z, and in that sense, even though the trajectory depends on these z's, there are always kind of collateral variables that exist, but you would not necessarily need to process them inside your multiple shooting scheme. So in that sense, your decision variables are still differential states and the inputs, and the z will not be part of them. Does it make sense? They're basically hidden inside the dynamics. And if your inequality constraints are not functions of z, here I wrote them in a very specific way, then again, you don't need to see the z's, you don't need to care about them. So yeah, in that sense, if you have an OCP of that form, you don't care about z in the cost, you don't care about z in the inequality constraints, then in principle, the z's will just basically live inside the integrators, and they will not appear in the NLP formulation at all. So is that the end of the story? Well, not exactly, of course. You may actually want to care about z in the cost and the inequality constraints. So what if you actually have that? So you also account for the z in the cost and the inequality constraints. You can think of the pendulum example where z is essentially describing how much force you have in the cable. And if you want to limit how much force you have in there, you would want to impose a constraint on z. That's an example of why you may want to use these algebraic variables. If that's the case, then the story does not change that much. Actually, essentially what you need to do is ask your integrator to also report the algebraic variables. And these z's will become implicit functions of your x's, these red dots, and of the u's. But there are functions of these things. So in principle, you should let it or leave it to the solver to resolve that. So you could think of, for example, again, if you use a very basic integration scheme, that the integration scheme returns x plus in the end of the simulation, but also z plus. So you have a kind of a sample of z that you get from your integrator. And then you can use this guy inside your NLP. And you will still have only x and u as decision variables, and these z's will be functions of this x and u. So you can look at this xk uk as returning x plus, but also the algebraic variable, and then you impose the constraints on these variables. One remark maybe that is good to know in practice. So imagine that you have this example, the pendulum, and remember that I said the input is essentially a force that you put on the mass, right? That's how I describe my model. And let's say that we use piecewise constant input discretization as usual. So let's say that you have this input profiles. That's just an example. But bottom line is that the force I apply on the mass, if I select this input profile, is actually jumping around, right? It's like 10 Newton, 5 Newton, 6 Newton, something like that. That's my index 1 DAE. So the input enters here and is jumping around, and Z comes in here, and that's basically given by solving this linear system. What happens to Z if I simulate my pendulum with these inputs? It jumps around as well, right? And remember, Z is the force in the cable. If I exert like no force and then right after that I put a force in here, then of course the force in the cable will also jump, right? So contrary to the differential states, which are at least continuous, they may have kinks, but they are continuous. The algebraic states may actually jump around, and they typically do when the input jumps. So your algebraic variables can be discontinuous, and that's something to take into account in some contexts. For example, if you have inequality constraints, you essentially need to decide where you impose them because of the Z jumping. Try to explain that in a bit. Because, yeah, let's put it that way. If you impose constraints on the differential states, at convergence, that's your xk, and that's your xk plus 1. And remember that we typically impose the inequality constraints on the time grid, right? So at convergence, they match, right? The end of the integrator matches the beginning of the next one. So it does not matter if you impose the constraint on xk plus 1 or on f of xk uk, because it's the same thing. They will match. But when you play with algebraic variables, you need to decide if you impose the constraint on the z reported at the end of the integrator or on a z that would match the beginning of the integrator, because they jump around. For example, here, if you impose the constraint here, and then the algebraic state jumps over here, this will do no good for you, right? So you have some decisions to make on that side. So yeah, the question is, do you impose these constraints at the beginning or at the end of the shooting interval? And ideally, you should impose it on both because of this jumping effect. Yeah, here is an illustration. For example, if you impose a bounds on the differential states, it does not matter whether you impose it on the blue thing, the integrator, or on the red thing, the discrete state. But if you do that on the algebraic variables, say you impose at the end, then the beginning may be completely out. You would want to impose it both here at the end of the integrator and here at the beginning. It's a bit of a detail, but if you play with these things, you may have these kind of questions. Okay. DAs are very often treated via collocation schemes, actually. And I will go back a little bit to that and see how it's fairly simple to treat DAs in that context. So collocation, that's a refresher. We've done that before, but it's probably good to go back to this quickly. So if you remember, you have your shooting intervals, tk plus 1, the starting point of the simulation. Then you want to approximate your trajectories, this black thing here, via a polynomial, and you need to position these thetas so as to shape the polynomial to represent your simulation. So you try to approximate your trajectories by parameterizing this theta, there are a sum of these polynomials. There are Lagrange polynomials. And you have a bunch of conditions. So the first one is that your trajectory should start at xk. So your approximation should start at the right place, the one given by the solver. And then you have a bunch of equations that essentially say that your polynomial should satisfy here the implicit ODE at a bunch of points. So for example, this ones. So that was the philosophy. Here I'm using directly a collocation scheme on an implicit ODE. So that's my x dots, and that's my x, and that's my u. Now I'll replace my x dots by the slope of the polynomial at that point, and here by the evaluation of the polynomial at that point. And if you remember from the properties of this polynomial, I can replace this guy by a sum of the p dots and this one by the thetas. So that's what we saw a little bit on the collocation chapter. So we have this setup, and the way you would write down your NLP, in this case here you have a simple ODE. You have your initial conditions, then that's a shooting gap, and then you have the direct collocation constraints that will basically support the integration inside the NLP, and then you repeat that. So on every shooting interval you have that essentially this guy must match the xk, and the xk is itself also this guy matches essentially the end of the previous tail. So you have this construction, that's the shooting gap constraints essentially. Here that would be a direct collocation scheme with implicit ODEs actually. So that's f x dot xu. X dot is replaced by the weighted sum of the p dots. These are the trajectories on the different checkpoints in the interval. And you have this the set of decision variables. So the xk's are replaced by all these thetas in the solver. Is that okay? You remember this stuff? Yeah. Okay, what happens now if I need to introduce a dA? So I have a f that will somehow be solvable for giving x dot and z, provided that x and u are given. And I'm going to try to build the same collocation scheme, but now having z on top. So what happens actually is that you keep the same stuff for x, and you will also build a polynomial for z in some sense. I'll not detail that too far. But that's the same story. You're using the same polynomial, and I have a set of discrete variables, z, k, i, shooting interval k, checkpoint I, that will basically describe my z trajectories. So on the checkpoints, my x trajectory is basically given by the theta ki's, and also on this checkpoint my z trajectory is given by the z ki's, these parameters here. You have k plus 1 degrees of freedom for the differential states. So your theta ki, I goes from 0 to k, so you have k plus 1 of them. But for the z, you actually need to go from 1 to k, not from 0 to k. So you have 1 degree of freedom less in the z, or one parameter less in the z. Do you have any idea why? It's really not obvious. Well, the explanation is here in some sense. The first theta k0, this guy here, you will use it to enforce continuity. So you want the end of that polynomial here to match the beginning of that one. So you need 1 degree of freedom to make your trajectories continuous. As we've seen before, the z can jump around. You don't need a degree of freedom to adjust the trajectories and make them continuous. You only need them to enforce the DAE on the checkpoints. So you don't have a degree of freedom here for Z. If you have one, then your code will not work because you will have unused variables. So that's a detail that is important in that context. If you fully unpack the collocation equations, you also realize that you don't need this degree of freedom. Okay, so we have differential states, algebraic states, the interpolation scheme, and then the collocation constraint would basically look like this. You have a set of equations for enforcing continuity, that's the shooting gaps, and these constraints would describe or solve the dynamics of your DAE on the checkpoints. Now you have these extra variables, the zki's, that enter in here and will support the solving of these equations. So they turn into this, so shooting gap constraints, that's the theta's matching, and the dynamic equations reduced to that. And that's another way of understanding why you have 1 degree less in the z's. You have an extra equation for the thetas, which involves the theta 0 in some sense and the theta k of the previous interval. And you have, in one equation here and k equations here, and the z's are only involved in this equation. So if you have k plus 1 z's, you have 1 too many because it will not appear in the equations anywhere. Okay, if you ever apply these schemes on DAEs, you will quickly realize that or hopefully quickly realize or remember that you need to do that. If you have semi-explicit, it's not different. That's the semi-explicit DAE, x dot equals f, 0 equals g of x zu. Again, it's always the same philosophy. You replace x dots by this thing here, and the x and the z's by these variables. So it turns into this set of equations. So if you have to form an NLP for direct collocation with DAEs, so you have the initial conditions, shooting gaps, and then you have your dynamics with the z's appearing now in here, and you have these guys for every shooting interval. And then in your variables, you have the thetas for supporting the differential trajectories and the z's for supporting the algebraic trajectories. Semi-explicit DAEs, same story almost. You would then write the ODE part and the algebraic part, and that's it. And in some sense, you can look at your z variables as extra inputs in the system that are needed in order to resolve this equation g. So implicitly z are given by g, and then they will influence the dynamics. And that's one way of looking at it. Yeah, that's a bit of a detail. You have different collocation schemes, Legendre and Radau. In principle, for DAEs, you should use the Radau scheme, but it has to do with some fairly intricate questions. So Legendre is the one that does not have a checkpoint at tk plus 1, and Radau has a checkpoint there. In practice, it actually works with both, but in theory, you're supposed to use Radau. Yeah, that's actually, we mentioned this thing in the collocation lecture before. If you're not happy with the accuracy of your integrator, increasing the number of Ks, the number of checkpoints, is typically not the best thing to do. It's often better to reduce the main time grid, so tk plus 1, introduce more intervals rather than increase the order of the polynomial. If you use high order polynomials, you tend to have bad linear algebra in the solver. That may not really help you. Okay with that? So, well, bottom line, if you have DAs, collocation schemes work very well. Just have a few things to be careful about. Okay, I'll probably finish that tomorrow, but I wanted to discuss, because many people are playing with flying stuff. So talking a bit about optimal control over SO3. SO3 is like the Lie group associated to rotations. And yeah, it's a bit of a few details. If you have 1 hour to waste at some point, you can read a bit about Lie groups. It's actually quite interesting. And the rotations are part of these things. You have a number of things related to the structure inside these groups. But the bottom line is you can think of rotations as a specific object in a group. The interesting thing is that, yeah, okay, that's maybe a bit too far, but the rotation matrix itself is not the rotation itself, if you want. So the same way as vectors become a list of numbers only once you have a reference frame, the rotations become, or the rotation matrix becomes a rotation only once you have assigned a reference frame. So that's what I'm trying to say here. Anyway, for example, if you want to represent the orientation of an aircraft, one way to do that, so of course you can use angles, like the 3 rotation angles, and the rotation group has 3 degrees of freedom, so you can in principle do that. Does everyone know about singularities in the Euler angles? Yeah, okay, that's known. So most often, if you want to be safe in this context, you want to use either quaternions or the rotation matrices directly. It solves a lot of problem in modeling these systems. And I'll explain a bit later, but we tend to use the full rotation matrix for representing rotations when we do optimal control. And in that sense, essentially, you take the 3 leading vectors of the frame attached to your aircraft, and you basically express these vectors in the Earth reference frame, and you get your rotation matrix made of 9 numbers. You can put them in a 3x3 matrix. You could also put them as a list of 9 numbers. And then the dynamics become very simple, because it's R dot is given by R times this matrix made of the rotation velocities around these 3 axes, and it's a screw symmetric matrix. So it's a very specific structure. But here the dynamics are very simple. It's bilinear, right? If R is part of your states and omega is part of your states, you're basically just having multiplication between states, as opposed to, for example, having lots of sines and cosines if you have Euler angles. And quaternions are also a little bit more nonlinear than that. But then you have consistency conditions. Again, it's kind of the same thing as for DAs. These dynamics make sense only if you make sure that your rotation matrix is a rotation matrix at least somewhere on the trajectory, for example, on the initial conditions. So R transpose R should be identity, essentially. Otherwise, your rotation becomes something nonsensical very quickly. Okay with that? Simple stuff. Yeah, I'm just showing that as a quick example. So if you go for Euler angles, the dynamics read like this, so more complex, sines and cos all over the place. You don't have consistency conditions, and then if you want to make changes of reference frames, for example, you have a velocity in the fixed frame, you want to bring it into the aircraft frame, then you have this awful stuff that comes for transforming the vectors. So you have very complex expressions, no consistency, but you have complex expressions in the dynamics and whenever you do changes of reference frames. Quaternions, it looks like this. The dynamics are not that complex. You have also some consistency conditions, and if you have changes of reference frame, you need to form this trilinear product. So you have essentially terms that involve three multiplications between different states typically. So with this matrix, that matrix, and maybe your velocity. Yeah, you probably know that. So the quaternions can be a bit annoying to work with. For example, for a given orientation, you have two quaternions that represent that. So it's a bit sometimes a bit annoying. Yeah, also in optimal control, you have to deal with that. If you make a full rotation, then your quaternion will flip. And if you impose some conditions on your orientations, you maybe get awfully lost from that effect. And the so-called direct cosine matrix, or using R directly, everything is bilinear in the dynamics, in the consistency condition and changes of frame. So it's pretty handy. Yeah, so that's I'm not sure which is better between rotation matrix and the quaternions, but that's what we tend to use at least. Okay, so you can discuss a bit this consistency condition if you do optimal control. So if you enforce the initial conditions again, so say you have a matrix R0 where the system is supposed to start, so it's given orientation to start with. Then you can essentially impose that as constraints, and maybe you have other stuff like your dynamics and so on. And then all that matters is that the R0 that you assign, your initial conditions, you need them to be consistent, right? But as long as you do that, your R will remain a rotation matrix throughout the dynamics, right? So in this case, it's simple. You could also impose terminal conditions that are consistent, that would have the same effect, or you can impose some condition anywhere at any time that would keep R as a rotation matrix. Now, if your rotation matrix, if you don't have such things, you don't have assigned initial or terminal conditions, then it's not completely obvious how this R will have respect the consistency conditions. Here is an example of problem. You can imagine this guy would be called a periodic problem, for example. So you want so the problem goes from 0 to t, and you want the orientation you start with to match the orientation you finish with. So it will be like a periodic maneuver. You want to come back where you started. So you could impose that by saying I want my R at time 0 to match my R at final time. That would be this constraint. So it would be like flying like a turn and coming back where you started. But if you just impose that, then nothing is saying that R should be a rotation matrix. The solver would choose anything it wants. So you also need to impose the condition that your R is a rotation matrix. And you could do that by saying, well, I could impose my consistency conditions at, for example, time 0, right? Does it make sense for most? Yeah. So that will be a periodicity constraint and a consistency condition constraint. Maybe you have also other dynamics. Maybe it's a complete aircraft. Now, if you do that, you have a problem. Maybe your solver will survive this, but if the problem is a bit difficult, it may just crash in flame. I don't know if you see why. It's not obvious at all. So essentially what's going on is you can essentially count how many constraints you're imposing. So R is 3 by 3, so it's 9 numbers. So if I write this, I'm writing 9 constraints, right? So I have 9 constraints here. And well, this is pretty much the same. It's also 9 constraints. R transpose R is a 3 by 3 matrix minus identity. That's also 9 constraints. So this is imposing 18 constraints. But the problem is this rotation matrix itself. Let's imagine that omega is solved, and you have your inputs and everything. So all the states are solved, but now you're asking how many degrees of freedom you have in picking R0. And well, R0 is a 3 by 3 matrix, so you have 9 numbers to pick here, right? So essentially you're imposing 18 constraints on 9 degrees of freedom. That's 9 too many, right? So you actually have a problem. It's not completely obvious. You need to think a bit about it. But the bottom line is that you have 9 constraints too many, and you need to pick them for elimination. You need to eliminate 9 constraints. And there you could, in principle, do a number of things. Some people would do in practice is, for example, impose, if you think about that. So you have 9 numbers. So if you think of your 2 matrices like this, some would say I'm gonna impose maybe only 3 of these constraints, maybe these ones, and on my R0 transpose R0 minus I, that's also constraints in a matrix form. I'm gonna impose these ones, for example. So I've removed 6 constraints here and 3 here. I'll remove 9 constraints. And that may actually work to do these things. But you need to eliminate these constraints. There's a bad news, though, is that regardless of how you choose to eliminate constraints, there will always be a configuration where you still have constraints that are not completely independent. So having too many constraints for not enough degrees of freedom, that's an LICQ problem. You have dependent constraints, so it will basically screw up your solver. Once you eliminate your constraints, you would have 9 degrees of freedom for 9 constraints, but you may still end up in a problem. So you may have that the system turns into a way that makes 2 constraints again linearly dependent, and then your solver will suffer from that. Yeah, this stuff is not really obvious, and actually it took us a while to fully understand these questions. It turns out that you have the same problem for index-reduced DAs, and in that context, it's a tiny bit easier to understand the problem. So if you had periodic optimal control with index-reduced DAs, that's kind of the same story. You have your DAE, you have some consistency conditions that you need to impose on your initial conditions, maybe, and then some periodic constraints. So you start and end at the same point. For example, on the pendulum, you could say, I want my pendulum to swing back where it started, so all the states would match. And I also need to impose these consistency conditions, otherwise the pendulum is like drifting away from where it's supposed to be. And there you have the same story. If you write this pair of constraints, both consistency and periodicity, you also have an LICQ problem. And it's really not necessarily very obvious, but maybe in this case you can somehow understand what happens. So the consistency conditions are essentially kind of pinning the pendulum on this ball here, right, at the correct distance. And what we know is that if you start the pendulum on this ball, it will, by the dynamics, stay on that ball, right? So in some sense, even though X has actually 6 degrees of freedom here, it can only move on that ball. So actually you have only 4 degrees of freedom, the position and velocity, right? If you think about angles, you would actually have 4 states, right? 2 angles and 2 angular velocities. So physically you have 4 degrees of freedom, but you have 6 variables describing that. And this guy will essentially remove enough degrees of freedom to make sure that it stays on the ball. But so you start with the consistency conditions that keep you on the ball, the dynamics will keep you on the ball, and then you impose again that you should end on the ball by matching the initial and final conditions. Maybe you can have an intuition mechanically of why you have too many constraints here again. It turns out that the mathematics explaining and packing this problem for DAs and the problem for SO3, it's exactly the same. It's the same math that explain both problems, and it's a matter of invariance in the dynamics. And you can resolve these problems using similar techniques. And it's a little bit barbarian, but we got this paper out this year actually explaining all this stuff properly. A few more minutes just to finish that. Okay. So here is an example of a problem where we use all these techniques. Maybe it's interesting for some guys doing flying stuff here. So this airborne energy stuff. It's a new version of WinEnergy. It may never work. I don't claim that it's a good idea, but there is money to research on it. And the idea is to have a kind of a UAV linked to a cable, and it's kind of doing these flying patterns in the air, and the wind would be blowing like this. So it's basically like a kite flying in the air, and you have ways of extracting energy. I don't know if I have a video. No. Extracting energy from the wind by flying in these circles. One way is to have basically turbines on the UAV, and you transfer power to the ground. So there are actually companies building prototypes in the megawatt scale now. Maybe it's gonna work. But the bottom line is that you have a periodic optimal control problem here. You want to maximize the energy that you harvest, or basically the average power that you harvest on this trajectory, and it has to be periodic. You want to come back where you started. And it's a fairly complex system, and you have a lot of physical effects that you need to trade on to maximize your power. So it's really not a system that you could easily guess what is the correct trajectory to fly. So you can form that as an optimal control problem. So we use this kind of approach I described with the pendulum. So we describe this guy as a completely free-flying thing with position and velocity, and you have the rotation matrix, and then we add the cable that forces this thing to be at a specific distance from the attachment point on the ground. So long story short, the model equations look like this in using a DAE technique. There's actually a paper. That's an interesting thing. If you describe everything using angles, that would be like the classic engineering approach. So you have like an azimuth and an elevation angle and describe everything in this form. There's a paper showing the model equations you get, and you have 11 pages of equations in A4 format. So that's a bit more compact. But then you have to resolve these consistency conditions. You need to resolve that the UAV starts at distance L from the origin. You have this constraint. That's the consistency condition for the DAE form, index reduced. And then you have the consistency condition for the rotation matrix, and then periodicity for the rotation matrix, and then periodicity for the position, velocity, and angular velocity. And then you have some inequality constraints. So the OCP looks like this. And this function here, that's the forces you have in the aerodynamics, F and M, forces and moments. There are fairly complex models behind that. Okay, but you can write this down, for example, in Casadi or any solver, and throw this at an NLP solver and get flying trajectories that maximize the power you harvest from the system. We have to use homotopy strategies in this context. If you just throw the problem in there, it will never work. So what we start is by asking the solver to, for example, fly a trajectory, find something feasible, maybe like just a tracking problem. So we start the NLP with an objective function that is fly this circle. And we also start the problem with introducing our own forces and moments in the model. So we basically control completely the flying machine here. And we solve that first. And then we have a parameter that slowly phases out these forces and moments to replace them by the correct one, the aerodynamic ones. So our forces and moments disappear from the model and these guys appear. That's called a homotopy strategy. And if you do that, you actually manage to solve the problem. Well, actually you don't, because if you write the problem like this, here is a report of what happens. That's IP opt, so it does not really get much better. And we have the homotopy strategy. So each of this point here reports a step in the homotopy strategy. So we go from the simple problem here, and we try to move towards the more complex problem. And that's the number of iterations IP-opt used to try to solve the problem. So it starts with a few dozens here, and then we jump to 10,000, and then we are above 10,000, all the way to 100,000 iterations to solve the problem. And there it crashes. Now, after a few hours, it's just giving up. And all this difficulty comes entirely from these constraints that are not sufficiently independent. So you can apply these tricks, and the paper is very barbarian, but at the end of the day, they are fairly simple. You need to remove these constraints. You need to project these constraints into a lower dimensional space. Here the P's are the basis for the symmetric matrices. By this I mean scalar products on the matrix space, or traces essentially. You need to do something with this guy as well. Here you do a projection on the space orthogonal to this guy. What is orthogonal to symmetric matrices? That's the skew symmetric matrices. You have 3 of them, so that's 6 constraints, 3 constraints. So basically you go from 18 constraints to 9 by doing that. And that's the proper way of eliminating constraints. And then we do a modification here. That's a lifting actually. We actually introduce degrees of freedom here by having this extra variable and multiply it by this, and also lifting on that one. Why does it work? Well, that's a bit complicated to explain, but it works. So if you throw this problem, you resolve what you want. You resolve the problem, and this is the same graph as before. So the homotopy steps, it converges, and you never take more than 1,000 iterations. And these different things are, one of them is this exact procedure. You have actually a bunch of choices on how you treat this difficulty, which gives a slightly different number of iterations, but all of them work. And that's actually the outcome of the optimization. It's doing this nice flying pattern, like basically here it's a pumping mode system, so you transfer the energy by reeling out the cable. So it's the UAV flying away from the cable, and then it comes down here, retracts, and flies again. All right, yeah, I'll stop here. Yeah. Was that?
Do you have a video of the plane?
I think I could find that. We'll do the classic trick. Called YouTube. Let's pull this one. Yeah, that's the biggest prototype out there. Nah. Can stick to this format maybe. Yeah. I'm not sure. I think it's 0.5 megawatts, this one. So these guys are in California. There's a company in the Netherlands and a few in Germany also doing these things. So here this guy is using onboard generators. So you have small turbines and then power transferred via the cable. It's a bit of a crazy technology. I mean, I would not argue that it's gonna work, but it's fun at least. Okay, yeah, if you have any question or anything to discuss, I can be around for a bit.